Hi everyone, welcome to today's webinar. Our topic today is Resilience for Free, and this webinar is a presentation of Clean Energy Group's Resilient Power Project. And with us today we have Seth Mullendore and Rob Sanders from Clean Energy Group, and we are also joined by Henry Misas from Bright Power. And before we get started with our presentations, I'd just like to go over a few quick housekeeping notes. All of our participants today are in listen-only mode. You have a few options for joining the audio portion of our webinar. You can connect using your telephone or your computer mic and speakers, and there's some instructions on your screen for that. A very important note, please submit your questions as you think of them throughout the webinar by typing them into the question box on your webinar console and hitting send. We will be reading through your questions as you send them in, and we will be saving time for a Q&A with the audience at the end of the webinar. So type them in as you think of them. Don't wait until the end to write in your questions. And finally, this webinar is being recorded. You will find a recording of this webinar as well as all of our previous Resilient Power Project webinars on our website at the addresses that you see on your screen. So for our webinar today, we have three speakers with us. First up is Rob Sanders. Rob is the Senior Finance Director for Clean Energy Group. And following his presentation, we'll hear from Seth Mullendore, Project Manager at Clean Energy Group, and finally from Henry Misas from Bright Power. And following their three presentations, we'll have a Q&A with the audience, as I mentioned. So again, a reminder to type in your questions as you think of them. And first, I will be passing this over to Rob Sanders.
Great. Thanks, Samantha. Let me say a word in getting started about the Clean Energy Group. Clean Energy Group is a leading national nonprofit that works to advance clean energy technology, finance, and policy programs. CEG also manages the Clean Energy States Alliance, which is a member organization of state and municipal clean energy funds. Find out more about Clean Energy Group at that link there, cleanegroup.org. You're going to see that at the bottom of every page, every slide, so it is a subliminal message today. Our Resilient Power Project is generously supported by several national foundations, including the JPB Foundation, the Kresge Foundation, and CERDNA Foundation. We also work closely with a number of the national labs, including Sandia and NREL. The goal of the Resilient Power Project is to increase public and private investment in clean energy, in clean resilient power systems, and to help city and state officials to develop resilient power policies and programs so they can protect low-income and vulnerable communities. The initial focus has been on affordable housing and critical public facilities. We manage a technical assistance fund for pre-development costs to help project developers get deals done. I'll say more about that a little bit. So to learn more about the Resilient Power Project, there's that link there also, resilient-power.org, which has a lot of publications and previous webinar recordings. So solar and storage is getting a lot of press now about its dramatic growth. It's expected to be a $1 billion industry in the next few years. This growth in the solar plus storage industry is happening at the same time that electricity outages are also increasing. The Lawrence Berkeley National Laboratory recently reported that the reliability of the U.S. electric power system is getting worse over time due to increases in the number and severity of major weather events. Specifically, the frequency of the interruptions is increasing by more than 1% a year. It may not sound like enough, like a lot, but it's cumulative, and it has effect over time. And more surprisingly, the average duration of interruptions is increasing by more than 9% per year. And one troubling aspect of this is that extreme weather disproportionately hurts low-income and vulnerable populations, including the elderly and disabled, and those with chronic illnesses, and those who need supportive services. So we believe the challenge now is to bend the technology trend for solar and storage systems to serve public needs, not just to save costs for commercial and industrial customers, which is important, and we fully support, of course, but to serve public needs as well, so such as affordable housing and other essential services in low-income communities. A good thing is that we are now beginning to see significant public investment at the state level for solar and storage. We're seeing more than $400 million, for instance, in new state funds in the Northeast alone in the last 18 months. There are $76 million approximately that's been committed to solar and storage projects over the past year. As I said, our Resilient Power project is focused in its first year on affordable housing and community facilities. This work has been jump-started through the use of our Technical Assistance Fund to make project grants to design and assess the feasibility of resilient power systems in specific building applications. We hope to demonstrate the technical and financial feasibility of clean energy and storage in affordable housing and assisted living projects, not only in New York City, Chicago, Washington, D.C., Newark, Boulder, Colorado, but elsewhere as well. Similarly, we're working to demonstrate the feasibility of clean energy and storage for providing critical community services to community shelters, police and fire stations, hospitals, municipal buildings, wastewater treatment facilities, a whole range of applications. We're working with city officials across the country as they begin planning their strategies for achieving greater energy resilience. To do this work, we see our TA fund as an essential market development tool. These grants pay for third-party technical services to determine feasibility of projects. Initially in New York City, Chicago, D.C., and Newark, New Jersey, but we're looking for projects nationwide. The fund is, Technical Assistance Fund is available for projects across the country. In exchange for providing a technical assistance grant, we do ask that deal and financing documents are shared and that we require reporting of project performance for a 2-year period. It is through our support of these early projects that we're beginning to understand how the specific economics of a project are affected by different state and local policies, incentives, and the design of market rules. Our new report, Resilience for Free, that we're talking about today, for the first time uses project data for multifamily affordable housing buildings in 3 cities to examine the financial case for installing solar plus storage systems to support critical common area loads in multifamily affordable housing. What we found was that location matters. The economics of a project differ significantly depending on local policies, incentives, and market rules. Some of the findings are that solar plus storage can reduce operating costs, especially through its ability to manage demand charges. And that's true in markets across the country. Also, the project can be repaid in large part in certain markets with electricity market revenues that are available to energy storage. So you'll hear a little bit later from Seth on frequency regulation and other grid services that generate revenues. We also found that energy storage can actually improve the economics of standalone solar in certain markets, and that in certain markets, resilient solar plus storage can be developed at little to no net cost over the economic life of the project. So essentially, it's getting resilience for free. Of course, there are many challenges facing solar and storage projects. For instance, there are financing gaps in this early market. There are no standardized or few standardized system applications for different segments of buildings and markets. There's no performance track record that commercial lenders can look to when they're trying to underwrite projects. And these are typically one-off projects, and there's a high cost of doing one-off projects. So at this stage in the market, incentives and policies make a big difference in getting projects done. So let me introduce the two other speakers today. Seth Mullendore is a project manager for Clean Energy Group who is working primarily with the Resilient Power Project on technical and policy issues and on energy storage project development. Prior to joining Clean Energy Group, he was a Sustainable Energy Fellow with Union of Concerned Scientists. Seth holds an MS in Civil and Environmental Engineering from Stanford University. Also speaking is Henry Misas, a Senior Project Engineer and Solar Specialist at Bright Power, where he works on renewables and energy efficiency projects. His focus includes the design and implementation of solar systems, including solar plus storage. Henry's a BPI multifamily building analyst and has a BS in mechanical engineering from Yale University. So, Seth, I'll hand it over to you.
All right, thank you, Rob. And before I get started, I just wanted to point out, too, that the report that we're going to be talking about today, in addition to being available on our website, is also in the handouts tab in your dashboard for the webinar here. So feel free to open it up there as well. All right, so I'm going to talk a little bit about the economic drivers for solar plus storage right now, and then get into the analysis of 3 projects that we looked at for this paper. I'm going to go kind of quickly through the economic side so that we have plenty of time for questions at the end. Please feel free to ask, or you can reference the report. This information is in there in more detail, and some of the more information that we have available on our website as well. A little far. Okay, so the values of solar, people are pretty familiar with this. The main thing is to offset electricity consumption through generating kilowatt hours that are either consumed on site, or through a net metering program, or through PPA with third parties where you purchase that electricity. But basically, it's reducing the consumption that you're using from the grid. Another factor that's available in some markets through solar is the sale of solar renewable energy credits, certificates, and these are available in states that have carve-outs in their renewable portfolio standards for solar, and there's a value for those solar credits in that system, or they can be sometimes traded in other markets in other states for states that don't have them. There's also some incentives for solar, the federal investment tax credit, 30% credit. That also applies to storage when they're installed at the same time under certain conditions. And then there are certain state and local incentives that may apply to solar as well. Let me get more into the value of battery storage, which people are a little less familiar with and can be a lot more complex. This graph, just very quick, shows that storage can have a value to all different levels, from utilities and grid operators to commercial and residential consumers. Lots of different value streams, just a few of them mentioned here. What we're going to talk about today are the ones that we looked at in the report that are available in the markets today that we looked at for these properties. One of the big things to note is that in addition to where geographically it's located, energy storage, where it's located on the energy system is also important. This is a graphic from a recent report by RMI that looked at the economics of energy storage, and I wouldn't worry about all the different services that they showed. The important thing to note here is that the kind of pink circle, the behind the meter location, is where all the values that are possible to be realized by energy storage can only be realized at the behind the meter, that is customer-located energy storage. And again, that's the type of system we're going to be talking about here, systems that are located at a customer site instead of on the grid somewhere in the distribution or transmission system. So first of all, the customer value. Really, the big thing we're talking about here is demand management. So commercial customers, unlike residential in most cases, face 2 sides to their energy bill. One side is the consumption charge that everyone's pretty familiar with because it's how all residential properties are billed, and that's based on the amount of energy you use which is the kilowatt hours. The other side is the consumption, the demand side, which is based on the kilowatts you use. So if you were to turn on all the appliances, all the electrical equipment in a building, that would be your highest demand that you could ask from the utility. And the amount you build is generally based on the peak amount that you want for any usually 15-minute or 30-minute period over a billion period, which is often a month. So just to show that, you're looking at two different buildings here in this diagram. So building A uses a lot of energy all throughout the day. Building B uses varying amounts of energy, in the most during the middle of the day, at midday. So the two buildings, building A will have a much higher consumption than building B, but they will both have the same demand. So their demand charge would be the same because they hit the same level of peak demand. Even though A is hitting it all the time, doesn't matter. They face the same demand charge. So the thing that energy storage can do is you can shift that demand so that, say, in the morning when you're using less electricity, you can use more consumption to charge up your battery storage system, which you can then discharge at midday to offset that peak demand and lower your demand down to that new red dashed line you see there, which can lower your demand then for the month and lower the cost that you pay to the utility for your demand charge. This is just, again, showing this process is often called peak shaving because, like it says, you're shaving off your peak demand throughout a period. So those areas colored in red, those are basically the peaks that energy storage then discharges to meet those. So you're not drawing that energy from the grid. So as far as the utility sees it, it stops at that managed threshold level, and anything above that is met by the on-site energy storage. And this can amount to some pretty big savings. In this example, we're reducing the demand by 35 kilowatts. And if you face a $10 per kilowatt charge, that's over $4,000 per year. $20 per kilowatt, it's over $8,000 in annual savings for a relatively small storage system for a commercial property. So the other side of the value stream that we're going to be looking at in some of these projects is the value to the utility and the grid. There are a number of different things. There's demand response programs that utilities use to offset their peak demand and meet those needs. But we're going to be talking more about power system reliability, and in this we're going to be talking about ancillary services. It can cover a number of different areas, but for these projects we're interested in frequency regulation. Now these markets exist throughout the whole utility system, but in a certain area, which is the PJM interconnection, which covers much of the mid-Atlantic, the grid operator has a payment mechanism that recognizes the value of energy storage as a quick response and accurate resource. Basically what frequency regulation is, just very quickly, this schematic shows that the grid wants to operate at 60 hertz. That's the level of frequency where it's happy and it does well. If there's an imbalance, then the system starts to break down. Energy storage can act to offset both too much supply or too much demand, either by charging or discharging when the frequency shifts out of alignment, and by charging and discharging, it can then put it back into equilibrium. And energy storage gets paid for this service. So let's get into the analysis of the three projects. And again, if you have any questions, just ask and we'll address them in the time we have left. So we analyzed three different areas, Chicago, Illinois, Washington, D.C., and New York City. So Chicago is the first one we looked at, and we looked at the economics of solar-only systems and solar and storage systems to see how they compared. All the figures, all the cost estimates and the savings and revenue estimates for these are based on real-world projects that are being scoped out, and this model is looking at what the real-world economics would be for an affordable housing unit that in the range of, say, 100 to 300 units. And this is looking at just the common area loads for those buildings, not looking at the entire load because those are often billed at a different rate, the residential rate. So we're looking at the commercial side of loads, what the actual building owner faces. So you can see here, we'll get into this in a little bit more detail, but the payback for solar in Chicago is not very good. Installation levels aren't great, electricity prices are low, and the payback over 20 years for that, payback is over 20 years for that, which is the lifetime of the project that we looked at. Adding in storage, 200 kilowatt, 100 kilowatt hour system reduced that payback time to about 12 years. And this is because in Chicago, it's in the PJM territory, and the energy storage system can participate in the frequency regulation market and get payments for that. So that reduces the payback time, simple payback for this project. Adding a larger system, a 200 kilowatt solar with 300 kilowatt battery with 150 kilowatt hour lithium ion battery, reduces it even further to about 6 years. I'm sorry, I think I said the other one was a 200 kilowatt battery. It's actually 100 kilowatt, 50 kilowatt hour for the medium-sized battery. So let's look at this a little more closely in some of the graphs from the paper. So these two charts will show you a graph of the savings in revenue versus expenses over the lifetime of the project. And the dashed line is the cumulative project value. Now, these are just looking at simple terms. We didn't use a discount rate for various reasons. But you can see between the two graphs that there is a significant improvement in when the payback period occurs through adding energy storage to the system. You'll notice a dip at year 10. And this is when we have replacement costs for both the inverter and the lithium-ion battery. Included in these cost valuations are the initial costs plus all the operations and maintenance, insurance, and other expenses that are involved in these projects. As far as the savings in revenue, we're looking at, on the solar side, offsetting the consumption and the sale of SRECs into another market. And for the storage side, it's really the frequency regulation revenue is the big revenue potential that we're looking at. Again, looking at the report, we have the figures, the actual numbers to look at this, and you can get a better idea. We included two different size energy storage systems for this project to show the economics of scale when it comes to energy storage and frequency regulation. Because not all of the costs of the storage system scale with the size of the system, the bigger storage system that you can have with a project, the better the economics often look. And here you can see between the top and the bottom charts that the payback is significantly better when you have the larger system. I'm going to move on to Washington, D.C. now. For this, we just looked at solar and then one size battery system, since we already showed what the economics looked like with different battery systems. Washington, D.C. is also within the PJM territory and therefore can participate in the frequency regulation market. The difference between Chicago and D.C., the big difference you'll see is in the solar payback. Instead of taking over 20 years, it only takes about 3.5 years. This is mainly due to the fact that Washington, D.C. has some very aggressive solar targets, and SREC prices are very high in Washington, D.C. And through sale of the SRECs, it makes the solar economics look much better. Adding the storage system into it didn't decrease the economic value or the payback period of the project at all. It's a more expensive project, but it takes about the same time to pay the project back. It's shown graphically again here. You'll see they have about the same payback time. And although the initial costs of the energy storage project are greater, you can see that the cumulative project value over time is also greater. So you get a greater overall return on the project when you add energy storage into the system. Lastly, we looked at New York City. New York City is quite a bit different than the other two. It doesn't have a frequency regulation market where energy storage can competitively compete in the market. So the only way for energy storage to make an economic play in New York City through our analysis was through demand management. New York City also doesn't have any incentive programs specifically targeted at storage. It has some storage incentive programs, but we found those to be uneconomic for the project that we were looking at. And we also used a much smaller solar size system here due to the rooftop constraints that a lot of properties have in New York City. Some perhaps in the outer boroughs, they have ability to add more storage to the rooftops. We were limited to a 30 kilowatt solar system based on the size that we were seeing in projects we looked at. So New York City does have a solar incentive through NYSERDA, and that solar incentive makes the economics of the solar power pretty good. We're looking at just over 4 years for the payback. When we add energy storage, a 30 kilowatt, 60 kilowatt hour lead acid battery, the economics don't improve in this case. They get worse. And you'll notice that we're using lead acid in New York. And this is due to the siting regulation constraints and fire codes that exist in New York City. They make it very difficult, if not impossible, to site a lithium-ion battery indoors within the city. So we had to use lead-acid batteries based on current conditions in New York. You can see graphically here, again, these two projects. The difference in we now have two dips in the lower graph. One is for the replacement cost of the inverter, again, at 10 years. The one at 7 years is for the replacement cost of the lithium-ion battery. Lithium-ion batteries, the lead-acid battery. As opposed to lithium-ion, lead-acid has a shorter expected lifetime. So we had to replace the cost of that at 7 years. Now, the offsetting demand charges in the system with the lead-acid battery, it did help offset some of the cost of having the battery over time. And you can see that the overall solar and storage project did have, favorable economic payback over the lifetime of the project, but not nearly as good as the other two systems. And the economics just didn't quite look as good in New York City. I wanted to talk about that just a little bit here in the end, and then I'll hand things over to Henry. One thing that we pointed out in the report is that some places like New York City, or New York State actually, that have a clear need for resiliency, as we saw after Hurricane Sandy, may need some incentive programs to be put in place and be targeted towards resilient solar and storage systems. And we recommend that the incentives should be high enough to encourage development, but New York is trying to move towards more market mechanisms for their solar and renewable energy and storage development. And we see that and think that it should decline as the market matures. This is being done in California with their self-generation incentive program, the SGIP program. So it doesn't need to stay at a high level as the market matures. We also think that the time, and discharge constraints should be limited. There's currently a program through Con Edison that incentivizes storage, but because of time and discharge constraints, it's very difficult to economically take advantage of that program. That's what we found. We did not include in our analysis because the project economics just didn't work out when we tried to do that. And there also should be a priority for projects in low-income areas and facilities supporting low-income residents and other vulnerable communities. These are the communities that have the hardest time recovering from disasters, and New York itself, through its Reforming the Energy Vision process, has identified that there may be extra economic barriers to these areas, particularly low-income areas, to adopting these technologies. And they're really the ones that need it most when we're talking about lowering bills and increasing resiliency. So that's all I have for you. I'm going to turn things over to Henry, who's going to talk more about some of the technical aspects involved in these projects.
Great. Thank you so much, Seth and Sam and Rob. So I'll talk a little bit about myself and Bright Power, and then try to jump through these slides quickly so we can get to the questions. So Bright Power is an energy and water management partner for portfolios of buildings. We have a national footprint, and we have an office in New York City, which is our main office, and where most of our work happens. And we have an office in California, where we are trying to tackle the problem of water. Is a huge efficiency problem, but we, we're working out there with lots of multifamily building owners, and we're essentially problem solvers. So this need for backup power through clean energy, or enabled by clean energy and now storage, is a problem we've been seeing, and we were hit by Sandy, so we are very familiar with what can happen when there's no power in especially low-income housing communities. And that's one of our main areas of focus, is low-income housing, doing projects in those communities and helping those communities be more resilient and recover from disasters. Also, this also improves their bottom line, which is one of the main things of this report, is that these systems can actually help buildings pay for their energy bills. So to hone in on one of the themes of the report, after energy efficiency and after solar power, we think that energy storage is the next big wave. So solar and energy efficiency are are ingrained now in the way that we think about buildings. So we see storage as coming, as something that will, it's coming to age, and it's definitely going to be part of the conversation for architects, for engineers, for building developers, policy. We just think that we need to accelerate how we deploy storage in affordable housing, multifamily, and that includes facilities that are there to help people in need, elders and disabilities, etc. Veterans housing, another key example. So I'm going to talk about the applications, the technology, what we can do today, and what we see coming in the future. So let's get started. This is just simple schematic. It might be a lot to some people. I just want to sort of walk you through what we're seeing here. It's very conceptual, and it's actually not that complicated. It's essentially I would say a few pieces. Let's start from the left. Where you see that tower on the left that looks like a refrigerator, that's your lithium-ion batteries in a storage system. What's in the middle is your inverter, which is not that different from a solar inverter. It's the same concept. It's converting power from the batteries and putting the power into the building. So what's on the right is the critical loads of the building. That can be your elevator, your lighting, water pumps. Really important to have water, especially in New York City where buildings are tall, and you need to boost the pressure of the water up. And I also see telecom as being a key, technology or load that you need to power when there's when the grid is off and you're trying to recover from a disaster. And then so in this diagram you see the critical loads as a box, and then you see the rest of the loads of the building in a different place. So it's important to think about these systems as to what are you powering when there's no grid. So you're not powering the whole building because that would be very expensive to do. You need a huge generator. It's very hard to do that with just batteries. But you can certainly think of the critical loads as the key pieces of the building that you're protecting and that you're making sure they're working when there's no power. And the box on the top, the site controller, is really important to understand. These systems are intelligent. They're doing a lot of things that weren't available before. Now you're controlling the batteries to do grid services like frequency regulation, or you're controlling the batteries to do peak shaving. Without these, you don't have revenue streams. And so this is a technical issue, but it's also an economic issue. How do you make these systems pay for themselves? So putting this all together, this is essentially what a battery system is, just by itself. And I'm going to show you, if you add solar to it, it's just one more piece of the puzzle. And you can connect the solar panels to the same inverter as the battery. That way you're reducing the cost. So just keeping things simple and elegant like that means that the project cost per watt can be reduced. There's other ways to do this where you don't connect the batteries and the solar to the same inverter. And you can also retrofit existing solar systems with batteries. So there's also ways to do this, and there's a whole world out there that that is developing these types of projects. Now, what we're trying to do here is to bring this technology to multifamily buildings. So far that has been challenging, but we are pushing the envelope on that, and it's very doable. I get involved in conversations with architects and engineers that are developing buildings, and for example, they don't know that you can power an elevator with solar power. It's the way that people think about these systems right now is just it's just savings. That's it. But it's very doable. It's very possible to power key portions of the building with these systems. So I'll just keep on showing technologies and solutions that are out there today that you can talk with these vendors to get more information. You can also feel free to get in touch with me, and I get involved in projects all over the country, so I can speak about the different markets. I'm happy to give you some advice or tell you how I would look at the problem. This this photo that we're looking at here is a solution from a company called Demand Energy Networks. This is a lead-acid battery system. It's fairly large. It's you don't have to make it this big, or you can make it even bigger depending on how much space you have. And I'll show a picture of where they put one of these in New York City. So on the left, basically most of the racks that you see in this picture are the lead-acid batteries. They're advanced lead-acid. They don't vent gas, hydrogen gas, but at the same time, they need to be protected. They need to have a battery management system. Just to make sure that everything is safe. They need to be temperature controlled. There's technology considerations that you need to have. On the right-hand side, there's the inverter cabinet and the protection, the safety switches and whatnot. So this system that you're seeing here, this is what it looks like in a building. So this developer, they found space in a fairly large multifamily building in New York City, which you would, the first thing that they would say when you knock on their doors is, oh, we don't have any space for this. So what we have to do is to go in and start looking and prodding a little bit. And Demand Energy Networks found a space in the garage on the basement, a space that nobody was thinking for creating revenue for the building. So they got the space, marked it out, put some bollards, and this is what the batteries in a cabinet look like. And this system is operating and is providing revenue for the building as we speak. I'll speak about the batteries themselves. There's different technologies out there, and I want to make sure that you understand how the batteries are different, and that there's lots of considerations which developers can help you with, such as cost and how much energy you have and how they perform over time. So just really, really basics here. These two battery chemistries. So on the left, the Aqueon saltwater battery, which I really like, is this green. The greenest battery you're going to have. Nothing in there is hazardous or toxic. So you can, as they say, you can drink the saltwater electrolyte on this battery. It's made in Pittsburgh, and American company. It's all over the world at this point as far as deployment. So this technology is there to hold energy. So for long duration, 6 hours, 10 hours, that's where they excel. They're not meant to provide a lot of power. So I'll say that again. So you can rely on these batteries for holding a lot of energy over time, but you should not be designing systems with these batteries for quick jolts of power. Something like powering an elevator or a big motor. That's not what these things are designed to do. Another example is, as Seth was explaining about frequency regulation, that requires a lot of cycling and high jolts of power, charging and discharging. So developers that do frequency regulation use lithium-ion batteries, which I'll speak about in a minute, but they don't use bulk energy storage solutions like like these Aqueon batteries. So, on the right-hand side, we have the lead-acid batteries. Right? This is another provider. They're called GS Battery. They're a worldwide company. So they provide advanced lead-acid batteries. And lead-acid, I would say, it's kind of in the middle between bulk energy storage and rapid charging and discharging. But but the main thing about lead-acid is that they're cheap, or cheaper than everything else. And you can have a lot of them. So in places like like New York City, where we're doing things like demand response for a few hours or peak shaving for a few hours, these could be a good solution. They're holding a lot of energy. The other technology, which is right now, most of the grid-type battery development in the United States is lithium-ion batteries. And the reason for that is, they're a very advanced solution. They're very mature. They're all over the place. I mean, electric vehicles are using them. So, the cost of these batteries is going down significantly. So this technology is really, really good for cycling and for high charging and discharging rates. And that's why for frequency regulation, there's really the technology that's out there. And they have a place in multifamily buildings as well. They can be the workhorse that turns the loads on or off when the grid is not there. And then these technologies have a very long warranty, 10 years or maybe even more. So you don't have to be thinking about replacing them every 5 to 7 years. So just to wrap up, right now the go-to in the building development space to do backup power is a generator, or even at this point you can speak about combined heat and power, but essentially we're talking about a gas-fired or a diesel-fired combustion engine. And the newer, what we can do today with solar and storage is, I would say it's now an option to consider, and it can replace a generator in the right circumstances, and it provides benefits on top of a generator. For example, with batteries, you don't have to worry about field delivery because the energy is already there, and you can recharge the batteries with solar power. So in a situation like Hurricane Sandy, some places of the natural gas grid were cut off, because either Con Edison or National Grid, the utilities, they couldn't supply gas at the pressure required in those areas. So in those situations, having solar power is tremendous, a tremendous advantage, and being able to store it and use it. But the drawback on the batteries is that they can't provide power forever. So you need something like a backup generator when your emergency plan is to provide power for a very long duration, and you need the fuel. So it's a trade-off, and it's definitely a conversation, and there's ways to pair these technologies to work together, to fit the needs of the building. So it's definitely a conversation of, what is the backup power need? How do you plan to pay for these technologies? And what's the best technology for the, for the situation? And we're happy to have that conversation with you if you give us a call. So with that, I'll wrap it up. I'm looking forward to the questions.
Okay, well, we have a lot of questions. So I apologize in advance if we don't get to your question. We're going to try to answer all of them that we can, and we do have some leeway to be around a little bit past the hour. So if you can stick with us, we'll try to get to them as many as possible. Starting off, I'll address this one to Rob. There was a question about the Technical Assistance Fund. Wondering if it acts as a subsidy to attract developers to projects that would not otherwise be economically feasible.
It's not an incentive subsidy to write down the cost of a project, other than it's a means of determining the technical and financial feasibility of a project. So it's to scope a project, to help design it, to figure out what the pro forma would look like, and the dollars can also be used to try to identify incentives that might be available to reduce the cost of a project. But it's basically for feasibility analysis, to get somebody the information they need to know whether they can move ahead and implement a project.
Great. There's another question which I'll address, and then I'll open it up, see if anybody else has comments on, about municipal utilities and how they could support these types of projects, and if they may be uniquely suited for municipal utilities. One of the things about municipal utilities is that they tend to be smaller, and they tend to be, have the ability to be a little bit more progressive sometimes in dealing with the benefits of solar and storage, and being able to provide value to the system. So what a municipal utility could do is work with the energy storage system owners and the developers to try to be able to create these value streams that a larger utility may not be as interested in, or may not be nimble enough to take advantage of in the short term. Rob, Henry, do you guys have any thoughts on that?
No, I had a conversation with somebody in Maryland yesterday There's an interest from municipal utilities there in fact, they're moving ahead with energy storage as part of a range of clean energy solutions that they're trying to do on the Eastern Shore.
Great. So another one for Rob. I would think. Can you talk more about how financing can be repaid for energy efficiency and renewables on multifamily affordable housing? In this person's experience, they've found that repaying subordinate debt associated with the savings is difficult due to cash flow waterfall issues and financial structure of affordable housing projects. Rob, you want to speak to that?
Yeah, that's definitely a really fair question. What is meant there is that most of these projects in multifamily rely on incentives and subsidy, but there is financing being provided often by the third party who may own the storage system, solar and storage system. So many of these projects are being done by third-party ownership, and there the financing is often provided by, if it's an early-stage company who's doing the solar storage, for instance, Solar Grid Storage before it was acquired by SunEdison, they would have equity, private equity, that needed to see a return on that investment. So it was those investors who were repaid through these revenue streams and cost savings because they owned those investors owned the system. But that's a valid concern. The models that we describe here don't assume a certain ownership. It's really based upon what the internal economics of the system are that would provide revenue. But in reality, many of these systems are being implemented through third-party ownership.
So we have a question about the PJM's frequency regulation price. The fact that it's currently quite good, but the revenue's at risk. There's no long-term contracts, and there is a possibility that prices will drop as the market becomes more saturated with energy storage. The question is, how can lenders get more comfortable when underwriting this revenue stream? First of all, I would like to say that that's exactly right, that this is a market-based revenue stream. So there's always risk that goes along with that. And PJM lately has been looking at the possibility that the market is becoming a bit saturated, and they've been readjusting some of their mechanisms. But the price has held steady for a number of years, and developers that we're working with expect it to hold for a number of other years. So Rob, I think you have some insights on how lenders may be able to work with this, or how utilities can provide some more certainty in these prices.
Well, there are a couple of things that are happening. We're beginning to see price hedging contracts be structured for this price risk in frequency regulation market. Now, those are fairly expensive because of the uncertainty in what those prices would be. But the other thing is that presently, utilities are entering into agreements for frequency regulation already and rate basing some of that. So to the extent that third-party owners could enter into long-term service agreements with utilities, which to expand to distributed generation plus storage, the frequency regulation services that utilities are already doing, that would be an important thing to see for two reasons. One is that utilities don't have to own that that storage for frequency regulation. They can simply enter into long-term agreements for those services, which are highly financeable. You know, once a utility establishes that they're going to do that. But the other thing is that by having these as distributed generation and storage systems, the resilience benefit can accrue to communities. They can, you know, those storage batteries could be in public buildings, in multifamily parking lots. It could be so, and then those critical loads would be tied to those systems when the outages happened. So that's something that we're looking into and pursuing at this point too.
Great. So there's a question about peak shaving and if utilities are currently encouraging peak shaving, even though that brings less income to the utilities from demand charges. So I think that's kind of, it's a bit of a mixed bag as far as that goes. There are certainly utilities that are encouraging peak shaving. The program that I mentioned that Con Edison in New York was promoting, they're actually paying people to lower their peak demand through certain hours because it is cheaper for the utility to either pay less through less demand charges or to pay customers to reduce their demand instead of paying for that extra capacity that's needed, which often comes from peaker plants, which tend to be natural gas plants that are just expressly for the purpose of providing energy during that time, and the energy tends to be quite expensive. And those are when prices peak for the utilities during those times when they need to call on those. So yes, actually, a number of utilities are looking towards lowering the peak by customers in order to offset their costs. And we're seeing that actually quite a bit around the country, though not all utilities have looked into that as of yet. I'm going to direct this one to Henry. This is asking about whether the models that we used for this project require master meters for multifamily projects in order for the demand management to work.
Well, with master metered buildings, the challenge is that you have an aggregate of loads, not just on the common area, but you also have your residential loads. So after looking at a number of master metered load profiles, so minute-by-minute load profiles, I can tell you that master meter buildings are very challenging to do to predict when they're going to peak and when you need to charge or discharge your battery. And another thing with master meter buildings is that the loads are, when people come into the building and start turning on TVs and elevators start going up and down, the loads tend to be very long, so long duration. It's definitely challenging, but that doesn't mean that you cannot do peak shaving. It might mean that you can do less peak shaving, in terms of the capacity number, in terms of kilowatts, because you have to maintain that discharge for hours and hours. Let's say 3 hours up to 6 hours, for example. I've seen very, very commonly. And days can be different. So your Friday might be very different than your Sunday. On the other hand, like let's say a direct meter building, when you're just attacking the common area load, it could, and I'm just talking about multifamily here, it could be a much more straightforward daily cycle. It might just look the same every single day. Maybe Sunday's different. But it's definitely easier. The loads might be less duration. So, if you speak with a peak shaving battery developer, they're gonna really like if you're talking about a direct metered building that has a very high peak demand. And if you're talking about a master metered building, it's just a little bit different conversation, but they will still be open to it. What I would say is that, in our perspective, the way that we scope projects, so we think holistically. So peak shaving is just one of the tools that we have. In a master meter building, we'll think about peak shaving, but we will also think about something like a combined heat and power system that is reducing base load. So it runs all the time. So it doesn't matter, if there's actually an aggregate of loads is better for those systems. So, you have to be very careful about what type of configuration it is. But in our experience, battery plus solar can work in the two different scenarios, in direct meter versus master meter.
Great. So, question: do we have a database available that shows states, utilities, and rate offerings that have high peak demand? I'm assuming the peak charge billing rates. No, we don't have a database as of yet. We are currently working with Navigant Consulting to do kind of a survey of peak demand charges in areas where they may be economically viable for these types of projects. I can tell you that California, a lot of California utilities have high demand charges. New York City has high demand charges, but across the country, seeing this again and again, that demand charges often account for half of the bill when we're talking about commercial customers. Even in areas where the charges aren't that high, they still can account for half the bill. So there's definitely a market to be seen there. We had a couple of questions about the assumptions we used for SREC prices. I don't have those off the top of my head. I'm going to have to refer people to the report for those. And there was also a question, just a general one, about whether maintenance costs were included, and those are included in the calculations that we did. I'm going to address this one to Henry again. There was someone who wanted to know whether the battery chemistry, lithium-ion versus lead-acid, significantly affected the payback of projects.
Oh yeah, I mean the lithium-ion batteries are still more expensive than lead-acid, you know. So it changes things, but it's not easy to say if it goes one way or the other. It really depends on how you're going to use the battery. The lithium-ion batteries, you know, let's say if we're talking about frequency regulation, you know, even if they're more expensive, they're gonna pay back quicker because you're using them more for a grid service that pays a lot. And the lead-acid batteries, even though they cost less, if you use them for something like peak shaving, they're going to pay back a little bit longer time frame because, you know, peak shaving is producing less dollars per kilowatt than frequency regulation. So it's, you know, it really depends on how you plan to use the battery. You know, what I've seen is frequency regulation and lithium-ion is a very good economic case right now. I would do it if I had a building and I could put some batteries in it, and $1 million to spend. And in the peak shaving world, at least in New York City, I've seen both. I've seen lithium-ion being used and I've seen lead-acid being used. I've seen one business case with lead-acid that makes sense. It pays back within, you know, a reasonable time frame, 5 to 10 years. But again, it all has to do with how you use the battery. So it's also the install cost, but it's also the replacement cost. So, you know, some developers might argue that lithium-ion, even if it's more expensive up front, in the long run, it's going to be better for your economics because you replace them maybe in 10 years and maybe you replace them in 20 years. So it just has to do with the application and how much battery you're putting in. So in frequency regulation, you don't need 2 hours of battery. You don't need 4 hours of battery. You need half an hour to an hour of duration, right? So let's say for 100 kilowatts of power, you only need 50 kilowatt hours of battery. So even if the battery is more expensive, you're putting less of it in there. So that really helps the economics.
Okay, I see we're already over time here, but we are going to keep answering some questions. I don't think we have a hard stop from anybody here. So we're going to go a little bit longer, and we'll get to whatever questions we can over the next, say, 10 or 15 minutes. And those of you that can stick with us, great. There was one question, some confusion over how the batteries were described. There's some person that had said that it's 100 kW to 50 kW. Is that a range? Hopefully it said 100 kW, 50 kWh, because these are the two different aspects of the battery. The first is the capacity, that's the kilowatts, the kW, and that's basically the amount of power that the battery can push out or discharge at any one time to meet loads. And the second is the energy storage side, basically the kilowatt hours. So this is more on how long it can provide the load. So the first is how much it can put out at any one point, and the second number is how much it can do over a certain time period. There's also a question about details on what the PJM territory means. This is basically, PJM is an independent system operator, which means that they are the operators that control the Sorry, getting some messages. Sorry, they're the operator that controls the transmission system, and they cover a certain territory. For PJM, it's a lot of the mid-Atlantic states. It stretches basically from Washington, D.C. to Chicago, some bits and pieces here and there. But there are a few of those across the U.S., and there are a number of places that are not within that territory or not within any territory. So it looks like we're going to be losing Henry here. So any questions directed to him, I encourage you to reach out to him, or you can reach out to us, and we'll pass it along.
All right. Well, thank you for the opportunity, and yeah, take care. Bye.
Bye, Henry. Question on environmental hazards associated with lithium-ion or lead acid. I'm not a battery chemistry expert. Both of them do have hazardous materials that make up the components of the battery. So there's certainly concerns, like with a number of batteries, with disposal of those materials. But like I said, I'm not an expert, so I can't really get into the depths of what's involved as far as that goes.
I would say that there's a good after market opportunity with lithium-ion batteries that ones that have gone through the first economic life are used for other applications as well. So they're recycled or reused after their initial purpose.
Yeah, that's right. Great point, Rob. We're seeing that a lot with car batteries. So batteries for electric vehicles are being used in these stationary storage applications for their second life use. There's a question about the length of interruption that could be avoided with the size batteries that we were looking at in these systems. We did not look at the actual amount of time that these batteries could power critical facilities or critical loads in these facilities. The reason for that is it's highly dependent on which loads are going to be isolated and met with the battery storage capacity and how they're used over that time. So it's very difficult to put a time value on these. What we did was try to size the battery most efficiently, so it would be the proper size for the kinds of loads that would be supported in these buildings and the kinds of use it's going to be used for, whether it is the demand charge management or frequency regulation. But as far as the actual time, it's just so dependent that it was really hard to quantify in this report. But we are going to do another report that will be looking at those that we hope will be out next year sometime. A couple of people noticed that in the New York City project, we replaced the lead acid battery at 7 years, but we didn't replace it at 14 years, and that's right. The reason we did that was we were trying to be as realistic as possible in these projects. We're also trying to be a bit optimistic on that front. And in fact, that assuming that after the 7-year lifetime of that battery, hopefully New York had worked through its issues with lithium-ion, so lithium-ion batteries might be in place. Or even if lead acid were, that the technologies would improve enough to last the lifetime of the project, and also assuming that lithium-ion battery chemistries had improved enough that they wouldn't need to be replaced. But if that were the case, it would, hurt the economics and maybe make that project uneconomical, which is another reason we're hoping that New York figures out their lithium-ion battery issues. There was a question, someone pointed out that they had thought that the lifetime expectancy for concealed lead acid batteries was up to 20 years, which would improve the economics. And I'm not sure on the lifetime of the battery. I have seen that for some lead acid, but it depends on how the battery is used. Because these batteries are going to be cycled each day and discharged to a great deal throughout the day, that shortens the lifetime of the battery. So if the battery is just sitting there to be used for backup power, it may have a much longer lifetime than a battery that's being used to offset demand charges as well. So it's because of the way that the battery is used, the lead acid battery, that it has that 7-year lifetime expectancy. Another question about the frequency regulation market. If there's something similar in the West to the PJM market. There's the California ISO market. They do have frequency regulation, however, it's not really economical for batteries to play in that market. That market's going to, I think, perhaps be expanded to include some other Western areas. So it's possible that there may become a viable market there. And California's doing a lot of other interesting things that may allow storage to make an economic play there. Okay. Question about other states that don't have adequate incentives, like New York State. Really, that's almost all of them. Anywhere where the market mechanisms don't exist for storage to make an economic play, if you want to see development of those programs, you're going to have to see some outside funding, whether it's incentives or federal or state grant programs. There's going to have to be some outside investments to push them over that hump and get projects in the ground. You know, like we said, PJM is an area where the economics can be good. California as well, Hawaii as well. There are some places where they are good at this time, but most states will need a little extra help to varying degrees. Few questions here that definitely are more Henry-oriented, so I'm going to have to skip over them. Henry would know this as well, but we have some insight to New York City when they will have a timetable for lithium storage being able to be viable as indoors. You know, they're currently undergoing a study, as far as I understand, and hopefully are going to have initial results next year at some point. Now, what that means, you don't really know when they're going to be acting on those results. So, you know, at the shortest term, say early next year sometime, but it could be and probably will be longer than that. Okay, I'm trying to see what else we have here. Maybe take one or two more questions. Question about mixing battery types to get better performance. That has been looked into in a number of places. So there's a project in Rutland, Vermont called the Stafford Hill Solar Project that I would recommend checking out. It's a pretty cool project. It's a big solar project. I think it's 2.5 megawatts of solar combined with 4 megawatts of storage. Half of the storage is lithium ion, half of it is lead acid. The lithium ion is meant to address the more quick response frequency regulation and things like that on the utility system. And the lead acid is more for the longer duration resiliency aspect. The project is actually tied to a high school in Rutland, Vermont that acts as an emergency shelter. So that is something that people are looking into. All right, so we're pretty far over here. I think we've addressed most of the questions, and several of the ones that are remaining are more related to Henry's area of expertise. So I think we're going to shut it off for now. The webinar should be available online within the next couple of days, and I believe the PowerPoint presentations will also be available to people if they'd like to take a look at those. So. Sam, if you have any closing thoughts for the people that are left.
Sure, thanks, Seth. So we do have several upcoming webinars and other resources that might be of interest to the folks on the line. You can find all of that on our website, resilientpower.org. We also have a newsletter sign-up link on the screen there. And I'll just leave it with the contact info for our speakers today. And thanks, everyone, for joining us.